Hello, grade 10s. In today's lesson, we're going to continue with vectors and scalars. We got up to the point where we needed to define an equilibrant. An equilibrant is a vector that has the same magnitude but is opposite in direction to some resultant vector. And the point of an equilibrant is to bring the system into equilibrium. So the equilibrant has to be the same in magnitude, but opposite in direction to this resultant vector in order to bring the system into equilibrium. So let's look at this 80 Newton box. 80 newtons is the resultant force acting down on the box. Now, if there wasn't an equilibrant, then the box would move right through the table and onto the floor. However, the box is at rest on the table, so there must be a force that is acting on the box that is equal in magnitude, equal in size, but opposite in direction, and that brings the system into equilibrium, and that is the equilibrant. So the equilibrant force is 80 newtons up. If you add this resultant vector and the equilibrant vector together, then the answer will be 0 because by definition, the equilibrant cancels out the resultant force and brings the system into equilibrium. And equilibrium means that the resultant force is 0. Now let's go back to the head-to-tail method. But now we are going to look at the head-to-tail method where the vectors are not necessarily in one dimension. So we're going to look at 2 dimensions. We're going to start by looking at 2 dimensions where the 2 vectors are at right angles to one another, but we're also going to look at 2 dimensions where the vectors are not necessarily at right angle to one another. So let's start off with a vector of 4 units to the right and 3 units up. So we have to choose a scale, and then we're going to add the vectors based on their directions and the scale using the head-to-tail method. So we have 2 options because remember that the order in which we add up the vectors doesn't make a difference. So here we're starting with the 3-unit vector up and then the 4-unit vector to the right. And here we're using the 4-unit vector first and then connecting the 3-unit vector up to that. Either way, our resultant is going to be the same. Now, what's very important, and this is where my students often go wrong, is they do not measure this angle over here between the 3 and the 4 with a protractor to make sure that it is exactly 90 degrees. They like to do it by sight. And unfortunately, that is not a very good way to measure angles. So you must always use a protractor to make sure that you're not off even by 1 degree and that this is exactly a 90-degree angle. So the resultant vector is going to look like this red arrow over here, again, regardless of the order in which you added up the vectors. Now, how would you work out the magnitude of the vector? Well, you take your ruler and you measure the length of this line, and then you use the scale. How would you work out the direction of the vector? Well, there you're going to use a protractor. Now, when you measure the angle, the direction, you need to measure the direction of the resultant vector from the tail of the resultant vector. So based on the scale, I got a resultant of 5 units. That's just based on a ruler measurement. And based on the angle here, using a protractor, I got 37 degrees. So you would measure at the tail of the resultant vector, the angle within the triangle. But it doesn't end there, because you have to provide either the compass method or the bearing method here. And the bearing method is always an easier method to use. And that's what I encourage my students to use when they are going to give the direction of the resultant vector. So the easiest method for stating directions, the bearing method. So we go to the tail of the resultant vector, and that's in fact where we measured the angle. And if we want to state the direction based on the bearing method, remember, it's going from the north clockwise until we hit the vector. So the resultant vector is going to be 5 units, again, based on the ruler measurement and the scale, with a bearing of 053 degrees, because going from north to this point would be 53 degrees. 90 minus 37 gives us 53 degrees. Remember that using the bearing method, you always have to use 3 digits, so you can't just say a bearing of 53 degrees. You've got to put the 0 in front of the 53. Now, two-dimensional vectors, as I already mentioned, are not necessarily always going to be at right angles to one another. So if we consider vector A and vector B, they're not at right angles, but provided that we know their angles, we can still provide the head-to-tail method. So here's vector A, here's vector B, and the resultant is from the tail of the first to the head of the last. Here's another example. Here we've got vectors A, B, and C. So here's vector A, and here's vector B, and those two are at right angles to one another. But here, in this case, we have a third vector that is not at right angles. Again, we need to be given the angles in order to be able to put together these vector diagrams, and we're going to practice that in a moment. And then, how do you find your resultant? From the tail of the first to the head of the last. Lastly, before we go on to some practice examples, in a closed vector diagram, when all the vectors are added using this head-to-tail method, the tail of the first vector starts at the origin and the head of the last vector ends at the origin. So if you take a look at this diagram over here, we've got vector A with an arrowhead. Then we've connected vector B's tail to the arrowhead of vector A. Now, if these were the only two vectors, then the resultant vector would be from the tail of the first to the head of the last. So the resultant vector would be in this direction. However, in this case, we have a third vector that brings the system to equilibrium. This is in fact a closed vector diagram because this third vector touches the tail of the first vector. Whenever we have a closed polygon, that means that it is a closed vector diagram, meaning that the system is in equilibrium. There is no resultant. So a polygon is created, meaning that the resultant vector has a magnitude of 0. Let's now take a look at some examples. And what I'd like you to do is, for each example, pause the video, try it on your own, and then go through the working out and the explanation with me. So the first one states, a squash ball is dropped to the floor with an initial velocity of 2.5 meters per second. It rebounds or comes back up with a velocity of 1.2 meters per second. Determine the resultant velocity of the ball. So the first thing we need to do here is choose a scale. And I always go for simple scales. So I chose a scale of 1 meter squared is equal to 1 centimeter, which then means that my 2.5 meter squared velocity will be translated to 2.5 centimeters on my ruler. And my 1.2 meter per second squared velocity will be equal to 1.2 centimeters on my ruler. The first vector that I drew was the 2.5 meter per second vector down. Using the head to tail method, I now need to take my second vector and connect the tail of my second vector to the head of the first vector. Again, the reason I don't overlay them is for clarity purposes, so that the person marking your vector diagram sees exactly what you're doing. So using the head to tail method, I have a 2.5 meter line. I then have a 1.2 centimeter line that represents my 1.2 meters per second. To find my resultant, I go from the tail of the first, here's my first vector, to the head of the last vector. I would then need to measure this line, and this line would need to measure 1.3 centimeters. And that 1.3 centimeters can then be translated to 1.3 meters per second. And in this case, it is down. The other thing that I just want to bring to your attention again is that when you label these vectors, you must label them not based on the centimeters. You can always put that in brackets if it helps you. But you must label them based on the vector value, which is the meter per second value. Let's look at the next example. A man applies a force of 5 newtons on a crate. Another man applies a force of 7 newtons on the crate in the same direction, and the crate exerts a frictional force of 2 newtons. Determine the resultant force on the crate. Now, one thing that we need to realize is that a frictional force always opposes the direction of the motion. So if one man applies a force of 5 newtons in a particular direction and another man applies a force of 7 newtons in that same direction as a 5 Newton force, this frictional force is going to be opposite in direction. Now, you weren't told if the force that the men apply is to the left or to the right, so it doesn't really matter. You get to pick, provided that the 5 Newton force and the 7 Newton force are applied in the same direction, and then the frictional force is applied in the opposite direction. Now, the first thing I'm going to do is pick a scale. I've said that 1 Newton is 1 centimeter, meaning that the 5 Newton force will be represented by 5 centimeters, 7 newtons by 7 centimeters, and 2 newtons by 2 centimeters. I'm going to start with my 5 Newton force. I have chosen the direction that the men apply to the crate to be to the right. So I have 5 newtons to the right, represented by a 5 centimeter line. And then I have 7 newtons using the head to tail method. So I add a 7 centimeter line to the head of the 5 Newton force. And then I have the frictional force, which is acting in the opposite direction. So again, using the head to tail method, I'm connecting the tail of this vector to the head of the last vector. I'm just not putting them one on top of the other, again, for clarity purposes. Now remember that the resultant is from the tail of the first, which is here, to the head of the last vector, which is here. And if I measure this line, it should measure 10 centimeters, which translates to 10 newtons. And that is going to be in this direction, which is to the right. Here we're looking at an example of two-dimensional vectors at right angles to one another. A frog is trying to cross a river. It swims at 3 meters per second in a northerly direction towards the opposite bank. The water is flowing in a westerly direction at 5 meters per second. Find the frog's resultant velocity. So I start off with my scale, where I've decided that 1 meter per second will be represented by 1 centimeter. Therefore, 3 meters per second will be represented by 3 centimeter line, and 5 meters per second will be represented by 5 centimeter line. I picked my first vector as the northerly vector. That's 3 meters per second to the north. So this is going to be a 3 centimeter line with an arrowhead pointing to the north. Now, very, very important is to make a mini compass or a mini Cartesian plane or a plus sign, whatever you want to call it, at your starting point. This allows me to measure with a protractor that this is exactly a 90-degree angle. That is very, very important for the accuracy of my vector diagram. I then attach the 5 meter per second vector to the head of the 3 meter per second vector, starting at the tail of the 5 meter per second vector. I must use a protractor to make sure that this over here is exactly a 90-degree angle, because the angle between north and west is exactly 90 degrees. Again, that is key for accuracy. To find my resultant, I draw in my resultant vector from the tail of the first vector to the head of the last vector. I then used a ruler and I got a length of 6 centimeters, which translates to a resultant of 6 meters per second. That is the magnitude of my resultant vector. What about the direction? So for the direction, I need to go to the tail of my resultant vector and I need to measure an angle. Now, I previously mentioned that you should measure the angle inside the triangle, and you can. It doesn't really matter in this case because I have made a mini Cartesian plane at the tail, which allows me to measure either angle. Now, this would be a 30-degree angle, meaning that this angle over here would be a 60-degree angle, because 60 plus 30 makes a 90-degree angle. Now I'm going to use the bearing method to state the direction. Now I go to the tail of my resultant and I make a mini Cartesian plane or a mini compass because I need to find the north. Now the fact that in this case my mini compass is overlain with my first vector, that's not an issue at all. But this line over here represents the northerly direction. And from there, to find my resultant, I need to go clockwise until I hit the vector. So in this case, it would be 90, 180, 270 plus 30. So that gives me a bearing of 300 degrees. Alternatively, if I'd measured this angle over here, which would have been 60 degrees, I could have said, okay, well, my resultant is going to be 360 minus 60, which is still obviously a bearing of 300 degrees. Let's take a look at the next question. Sarah walks to school by walking 600 meters northeast and 500 meters north 50 west. Determine her resultant displacement. So let's take a look at the vector diagram. The first thing to do is to create a scale, and I have chosen a scale where 100 meters is equal to 1 centimeter. Therefore, the 600 meters will be represented by a 6 centimeter line, and the 500 meters will be represented by a 5 centimeter line. The second thing I want to do is make a little compass and figure out the direction so I can see up front what directions I'm dealing with. Now, these do not have to be drawn perfectly to scale. The lines are certainly not drawn to any kind of scale, but I did measure these angles over here using a protractor. It's not a must. It just helps you to visualize what's going to happen in advance. Now, I know that northeast is exactly in between north and east. This angle is a 90-degree angle, so I need a 45-degree angle in between. I also know that north 50 west means north 50 degrees to the west. North 50 west may also be stated as 40 degrees north of west. Regardless, it means the same thing. But what that means, because this entire thing is a 90-degree angle, is that if this is 50 degrees, then this is 40 degrees. If this is 40, then this is 50, obviously. Now, remember, to start off, I need to make myself a mini Cartesian plane or a mini compass or a little plus sign, whatever you want to call it, because I need some point of reference from which to start measuring. Now, based on this diagram over here, I can see that my 6 centimeter line, which represents 600 meters, is at a 45-degree angle, and I can measure this 45-degree angle off my little plus sign over here. So here's my 6 centimeter line that represents 600 meters, exactly northeast, because this is a 45-degree angle. What I'm going to do next is I'm going to make another little plus sign, or a mini Cartesian plane, or a mini compass at the head of the first vector. Again, I need some point of reference from which to measure the angle of the second vector. I'm not going to be able to do it without making a little plus sign. Based on this diagram over here, I can see that I need to measure 50 degrees from here or 40 degrees from here. It doesn't matter, whatever is easier for you. So I have measured a 40-degree angle, and that line is going to be 5 centimeters long. And so here are my two vectors, my 600-meter vector northeast. And then using the head-to-tail method, I've got my 500-meter vector north 50 west. Now, to work out the resultant, I go tail of first to head of last. Here's my resultant vector. To work out the magnitude of my resultant vector, I need to take a ruler and measure the length. I got a length of 7.5 centimeters, which according to my scale is translated to 750 meters. That's the important thing to label. The bearing here is a little bit confusing because this resultant vector, this line, looks like it's facing to the north. But it's not exactly north. And I know that because I've got my little plus sign at the tail of my resultant vector. And measuring with a protractor, I can actually see that my 90-degree angle, my north, is going all the way over here. So there is an angle between the north and my resultant vector. That angle is quite small. It's 3 degrees. So that means that my bearing is 003 degrees, because remember, bearing is measured from the north clockwise until you hit your vector. Let's now look at the last example. A dove flies from her nest in search of food. She flies at a velocity of 2 meters per second at a bearing of 135 degrees, and then at a velocity of 1.5 meters per second at a bearing of 230 degrees. Calculate her resultant velocity. So the first thing we need to do is choose a scale, and I have chosen 1 meter per second to be represented by 2 centimeters, which means that 2 meters per second will be represented by 4 centimeters and 1.5 meters per second by 3 centimeters. How did I work that out? Well, 1 times 2 is 2, so 2 times 2 is 4. And in this case, I'd say 1 times 1.5 is 1.5, so 2 times 1.5 is 3 centimeters. So that's the first step. My next step is to figure out the directions. What is a bearing of 135 degrees and a bearing of 230 degrees? This is my north. And the bearing method requires us to move in a clockwise direction from north. So a bearing of 135 degrees means that from north I need to go all the way to 135 degrees. So from here to here is 90, and 90 plus 45 makes 135 degrees. So this here represents a bearing of 135 degrees. A bearing of 230 degrees again means that I need to go from north and go all the way until I hit 230. So this is 90 and this is 180. 180 plus 50 makes 230. So if I measure an angle from the south of 50 degrees, that actually gives me a bearing of 230 degrees. Now, this vector diagram looks a little bit complicated, but let's look at it step by step. I started with the velocity of 2 meters per second at a bearing of 135 degrees. So I made here a little Cartesian plane. And from here, I need to measure 45 degrees. Whether you measure the 45 degrees from here, obviously it doesn't make a difference. As long as it's a 45-degree angle, and this line that represents 2 meters per second should be 4 centimeters long. So there's vector number 1. Now vector number 2 needs to be connected at the head of the first vector, the tail of the second vector to the head of the first vector. So I go to the head of the first vector and I make a mini Cartesian plane or a little plus sign. And I now want to replicate this angle over here. So that's a 50-degree angle from here. And now I can make this line 3 centimeters long to represent my 1.5 meters per second. So here are my two vectors. My resultant goes from the tail of the first to the head of the last. Now, if I measure the length of this line, I get a value of 4.8 centimeters, which I can then convert to 2.4 meters per second. So that's the resultant velocity in terms of magnitude only. What about direction? So for the direction, I'm going to choose the bearing method. It's the easiest method. Now I need to have a little Cartesian plane at the tail of my resultant. And here's my little Cartesian plane. Now this looks very confusing, but over here is my north. And from north, I need to go in a clockwise direction until I hit my vector. Now, when I measured this angle here inside the triangle, I got a 38-degree angle. So that means that I've got 90 degrees plus this 45-degree angle plus this 38-degree angle, which gives me a total bearing of 173 degrees. Again, this one is a bit confusing because if you look at this little compass over here, this resultant is almost going straight down. So the angle here is not very big, which makes this kind of resultant angle quite confusing to figure out. But always remember, you go from the north and you need to measure your angle until you've hit your resultant vector. So in this case, it's 2.4 meters per second at a bearing of 173 degrees.